Okay. Yeah. So suppose your program is executing and it has all the data that it requires is in the memory. Let's say a matrix or an array, and that program is just going on summing elements of that array. It does not require any service from the kernel. So then your program is executing. But suppose at some point your program wants to do some output or some input, then it will require some functionality of the kernel, and only then the kernel we need to run. Okay. So essentially, we are now starting to discuss how the operating system works. Right? So how does this happen? That your program runs at some point, then operating system, and so on. So now we are going towards discussing how does the operating system work. Now, from now on, when we say like how does the OS work, essentially we will mean how does the kernel work, because the kernel is again the most fundamental part of the OS, giving some fundamental functionalities. So that is what is our interest. How will the kernel work? Essentially, kernel is interrupt driven. Right? So we had taken some analogies last week, and some of you only had said this term, so you have some idea. Maybe let's discuss more. So an interrupt is kind of a wake-up call to the kernel, right? So when some other program wants, or even it's maybe some device wants some functionality or some service from the kernel, it generates an interrupt, and interrupt makes the kernel wake up. That means some function in the kernel is invoked. Now, is there only one interrupt? No, there are different types of interrupt, and based on the type of interrupt, some function in the kernel will be invoked. Okay. More technically, interrupt is a signal or an instruction which can be generated by either some hardware component or some software component. Software component can be your C program. Hardware component can be like say some device like IO device, something called a timer, which we will discuss just after some time. So different hardware components or software components can generate a signal or an interrupt. The interrupt in turn activates appropriate kernel routines depending on the specific category of the interrupt. Of course, an interrupt from an IO device is not the same as interrupt from, let's say, your program which wants to do a particular function. So the kernel differentiates between the different interrupts. Usually a code is associated with an interrupt, which helps the kernel to understand what kind of interrupt this is. And depending on the specific category of the interrupt, some kernel routine would be activated. As I said, there are different types of interrupts. One type is hardware generated. And this hardware can be both external or internal. External means from IO devices. Like we have so many IO devices, keyboard, mouse, printer. Right, so it can come from one of those. Or it might be some hardware internal to the processor. For example, a timer or a memory access violation. Right? So even an internal piece of hardware can generate an interrupt. So these were hardware interrupts. The other category is a software interrupt. This usually a program generates. Again, a program may generate this intentionally or unintentionally. Say for example, your program can actually make a system call which should generate an interrupt. Or suppose mistakenly you have done a divide by zero operation. Then also some program, which is not your program, but some program will generate an interrupt because you have clearly asked for an illegal operation. Okay. So I hope you now try to connect these discussions with what you have seen till now, like even in PDS Lab or in the last 2.5 years. So you have written many programs. Try to connect what we are discussing to what you have seen in those times. There are certain reasons for which your program gets terminated. For example, you have seen segmentation fault, then you have seen divide by zero error, right? So all these things possibly generated some kind of interrupt, and the operating system started to run, and that operating system terminated your program, or the kernel terminated your program, because your program had asked to do something illegal, right? So there are these different types of interrupt, and basically when an interrupt comes, the kernel starts running. Now who can raise an interrupt or who can send an interrupt? It can be either some piece of hardware or some piece of software. Let's do a case study. Handling an IO request. Let us do a case study, which might make some things clear about what we are talking. Let us assume the setup shown in this picture. So you have a CPU, a memory, and several devices, each device having its own controller. Like disk has its disk controller. These all are nowadays mouse, keyboard, printer, all are usually connected to the USB ports. So a USB controller is controlling all these devices. Then you have a monitor which has a your core knowledge. What is this connection called? Just type in the chat. Just looking for one word. I'm just looking for one word. Yeah, a bus. And of course, we can say data bus, control bus, etc. But essentially, it's a bus. So this bus is connecting all these CPU, memory, and all these device controllers. So in a bit more detail, let's say that the CPU and the IO devices can execute in parallel. Let's say, right? So each device controller is in charge of a particular device type, and each device controller has a local buffer. So how will data transfer happen? Let's say an IO operation is, say an input or output is requested. So essentially, the data that is to let's talk about an output operation, a print operation. So the data that is to be output is currently in the memory. First, that data has to travel from the memory to the printer, so to the local buffer of the controller of the printer. In this setup, we are assuming that the printer is connected to an USB port. So the USB controller is the controller for the printer. And as said, each device controller has a local buffer. Right, so the data is initially in the memory, the data to be printed. It has to be transferred to the local buffer of the USB controller. And then this controller can print. Right? So someone will have to start this process, right? Most probably the CPU, but let's see. Most probably the CPU will transfer the data from memory to this USB controller, the local buffer of the USB controller, and then initiate the print operation. Now, when the operation is over, the CPU needs to know. So the device controller will send an interrupt to the CPU to indicate that printing is over. Let us assume this setup. Now the question is, how will an IO request be handled in this setup? So your program has issued an IO request. How will it be handled? Let's talk about different options. First option, we do not consider anything like an operating system. Let's say your program is the complete master of the whole computing system. So your user program makes the IO request. That means your user program itself transfers data from memory to the device controller, and your program initiates the IO. Now, as long as this IO is happening, you can say that the CPU remains idle because your program is doing the IO, right? It does not require any operations right now. So the CPU remains idle as long as the device controller handles the request. When IO is completed, the device controller sends an interrupt, then execution of your program resumes. This is perfectly fine. The IO would have worked. But the problem is this: underutilization of CPU. Okay, so we will discuss this point later. Still, basically, all these input or output devices are much slower than the CPU. Okay, so suppose you are printing something on the printer, which might take a few seconds also, or a few minutes even. Through all this time, the CPU is being idle in this scheme. So this is clearly not a good scheme. It leads to severe underutilization of the CPU. This scheme is usually called busy waiting. Right. So the CPU is kind of idle as long as it is waiting for the I/O to complete. So this is very simple scheme. You don't even need an OS. Right. The simplest scheme possible. But clearly this is very inefficient. So this is not a good option. What can be better? Let's go to a second option, which will use something called an operating system. So now your program will directly not start the I/O. Rather, your user program will make an I/O request through a system call. Once this happens, once your program issues a system call, by the way, your program may not directly issue a system call, like maybe you issue only a printf, but then the C library for you will issue the system call. Okay, just make it clear. I mean, we are not differentiating between these two cases, but yeah, I mean, your program or some other program on your behalf, maybe a library function, issues the system call. So once you have issued the system call, now control goes to the OS. So now OS does all these things. It transfers data from the memory to the buffer of the device controller and then initiates the I/O. So remember, at this point, your program is not running. Your program has done a system call and it is not running. Rather, the OS is running. And OS has the CPU allocated to itself. So it transfers data from memory to the buffer of the device controller and initiates I/O. Now OS knows that until you have printed this, your program does not need to run anymore because your program is waiting for the I/O to complete. So rather, the OS can allocate the CPU to some other program. Okay. So see, this is the major difference between the previous scheme and this scheme. In previous scheme, the CPU was idle as long as your program was waiting for the I/O to complete. But here, OS, since we have brought in the OS into picture, the OS is intelligent. It knows that your program is waiting for the I/O to complete, so it can allocate the CPU to some other program. Now, upon the completion of the I/O requested by your program, okay, please keep yourself muted, Narayan. Oh, okay. Oh, sorry, not Narayan, but someone. Yeah, okay. Okay, so yeah, upon completion of the I/O, again the device controller will send an interrupt. Again, because as interrupt has been sent, the OS will come into play. So then the OS understands that, okay, your program is now, your program is no longer waiting for the I/O. The I/O is done. So it may resume your program. Why may? Why not will? Any idea? I've written here, we have written here, OS may resume this particular user program. Why may? Why not will? Yeah, exactly what Mukul says. Again, let's not talk about priority, but there can be other processes. Most probably there are other processes in the computing system. So then now OS knows that your program is ready, but it may not start it immediately. Rather, some other program may be executing. After some time, your program will also get a chance to execute. Right. So remember, we had discussed this chess analogy, etc. And there we said that it may happen that multiple agents require your attention or the attention of the OS at the same point of time. So then there has to be some scheduling policy, etc. by which the OS will decide whom to allocate the CPU. Right. So it may resume your program immediately after completion of I/O, or it may resume after some time. But the key difference of this scheme with the previous scheme is that the CPU is being utilized well. Okay, I think there is a bit of an issue. The end part of this slide is not being visible. Anyway, okay, sorry about that. But okay, so this scheme is called multi-programming. We will discuss this later. I mean today itself in a bit more detail, but this scheme is called multi-programming. So the main difference between the previous scheme and this scheme is that the CPU is utilized much more. When your program is waiting for the I/O, some other program can run, and that is managed by the operating system. Okay. Now just one more option, which is so this option is much more efficient than the previous option. But you know, system engineers go on improving computer systems because we want systems to be much faster and so on. So the thing to consider is that in modern day systems, an even better scheme is used. I won't go into details, but let me give you just an idea. For that, first understand that in a computer system, possibly the CPU is the most important and powerful resource. So we definitely want to utilize the CPU as much as possible. Okay. So in this scheme, it's okay. It's much better than the previous scheme, but there is still one problem. The CPU is still engaged in a lot of operations in this kind of a setup, because usually what happens is that CPU does not. So suppose if you have given a large amount of data to print, usually that whole amount of data is not sent to the controller at once, but the CPU divides it, the OS divides it into chunks, and maybe one chunk is sent to the controller for printing. That chunk is printed, then the device controller sends interrupt, then the OS again sends the second chunk and so on. Right, so basically the OS needs to use the CPU for every chunk. So even this scheme is not nowadays preferred. Right, so this previous scheme which we discussed of interrupt driven I/O is fine for small amounts of data, but it has a high overhead for bulk data transfer such as disk I/O. Often we give to copy a 1 GB file from say one place to another, a movie or something like that. So for that kind of a bulk data transfer operation, this previous scheme is also not as efficient as we would like it to be. So hence modern systems used a third option called direct memory access. Have you come across this term in computer organization architecture, DMA? Okay, fine. Okay, fine. So DMA is kind of a sub-processor, you might say, like not as powerful or as versatile as the CPU, but it also has some capability, the capability to manage transfer of data between memory and a device controller with no intervention by the CPU. Right. So it is like an assistant to the CPU, which can do one job without further guidance. That is, if the CPU tells the DMA, hey, a large, say 1 GB data needs to be transferred, the CPU tells the DMA the memory location, like from where to start transferring, which driver to transfer to, which device to transfer to, and how much data to transfer. If the CPU tells this much to the DMA, the rest of the actual transfer job DMA can do itself without any further help from the CPU. So what is the advantage? DMA can take care of this operation. The CPU can be allocated to other jobs. As I said, the CPU is the most important, resource in the computing system. So you definitely like to utilize it. You would like to minimize the involvement of CPU in I/O operations. So a modern day system looks something like this. Again, this is just a block diagram. I am not trying to explain every detail here, but just see that this block has CPU, the cache memory, and this is the memory. So I think so. Since you have done COA, you know well what cache does, right? So cache and memory, there is this flow of data and instructions between the memory and the cache. But when the question is about using a device, let's say an IO device, there is this DMA, which can directly transfer data from memory to a device, direct memory access. Okay, and why it is direct? Why this term? Because the CPU need not be involved. So the CPU can simply initialize the process that transfer 1 GB of data from memory location this to the printer. It transfers, I mean, it sets up this job and the rest of the job can be done by the DMA. Meanwhile, the CPU can be allocated to other jobs. Okay, so this is what is mainly used. But again, so through these three schemes that we discussed, I would suggest you to take note of a few things. One is that IO operations often take a lot of time, and therefore we definitely do not want the CPU to sit idle when an IO operation is taking place. Second, the CPU the CPU is a very costly resource and we want to, utilize it for processing programs as much as possible. Therefore, we are okay with putting in some small other controllers, like say DMA or some assistants to the CPU, which can do maybe one job, but it can do it without involvement of the CPU. Right. So DMA is one such assistant to the CPU, where the CPU does not have to be involved too much in the data transfer. Right. So just keep these things in mind. We will discuss more. Okay. So that brings us to the end of the slide deck 1. I'll start the slide deck 2, but before that, any questions? Okay. Okay, let me answer the first question. First the question by Tanmay, does DMA use processor? No, that's the whole idea. The processor has to initiate the data transfer, but once that is done, the DMA can handle the rest without involvement of the CPU. Okay, so DMA does not use the processor. That's the whole idea, that the DMA will not need to use the processor. Okay, now the question by Ishan is interesting, and it's a very natural question. Does something listen for interrupts at all times? Okay, that's a good question, and it might look so, like we are telling that a program can issue an interrupt, a system call, etc. So who listens, or what does this happen? Okay, let me try to explain. See, what does the CPU do? So you have taken a COA course, right? What does the CPU actually do? It just executes instructions. Okay. So I think you have heard, in general, things like instruction pointer, program counter. You have heard of these things, right? Program counter, etc. Okay. Okay, please hold on to your questions for some time, because let me explain this question. Then I can again give you some time to ask questions. Okay. So yeah, so you have heard of things like the program counter. So essentially what the CPU does, every time it accesses Okay, every time what it does is it fetches the next instruction from the program counter. So the program counter gives the address of the next instruction. It fetches the CPU fetches the next instruction and executes it. Right? This much I hope you all of you agree. So now suppose your program issues an interrupt. That means that your program no longer will run, rather some kernel method will run. Understand that it is sufficient if the PC, the program counter, is now loaded with that function and that address of that kernel function. Then it can start running. Okay. Your program was running, so the program counter contained the instruction for, contained the address for your next instruction according to your program. Now suppose a system call or interrupt has happened. It is sufficient if the program counter of the CPU is replaced, is loaded with the instruction of a kernel routine. This much is handled. Now, if you say that something listens for interrupts at all times, I would not put it that way. But yes, there is some mechanism that an interrupt can occur at any time, and then control will move to some routine of the kernel. But I would not put it in this language that something is listening for interrupts at all times. Okay. So Moinak, do you want to add anything here? But because this is a very natural question or doubt. Moinak, are you here? Yeah, we are going to study this mechanism. Okay, not sure if Moinak is here. Anyway. Okay, let's proceed. Okay. Okay, I see another question by Tanmay, a follow-up question. How DMA works if it does not use processor? DMA is not a program like another C program. DMA is a device which can work without involvement of the CPU. Right, so DMA is not another program which needs the CPU to execute. Okay, a question by Debojyoti. If the CPU keeps on initializing data transfer, will the DMA queue the jobs if it has not finished the earlier data transfer? Okay, this is also a relevant question. This I am not sure what it happens in modern systems because there are multiple design choices. One is what you have suggested. The DMA can, the DMA may have the ability to queue the jobs. Fine. The other thing is that remember what was written in the previous slide. Upon IO completion, device controller sends an interrupt. So the DMA can also work in this mode. That the CPU knows that the DMA has been initialized with one job. When that job is over, the DMA will send an interrupt to inform the CPU that the job is over, and then the CPU can give another job. Okay, so there are multiple design options here. I'm not very sure what is exactly done in modern systems, but there are all these design options. Is DMA part of the motherboard? Again, I'm not sure if this question has a fixed answer. Okay. Motherboard is does not seem relevant to what we are discussing now, whether something is part of motherboard or not. Okay, but yeah, I'm not sure about whether this question has a fixed answer or whether different systems handle this differently. Okay, Ruta has asked a question. So compiler decides whether to call DMA. Okay, this question is I am not at all sure how this question is coming up. So Rutav, can you unmute yourself? Rutav, Mitesh, or can you unmute yourself?
Am I audible now?
Yeah.
Yeah. Okay. So
Yeah.
you said that for input output processes, DMA gets called, right? Instead of going through the CPU and processor. So how is it exact? So the compiler has to decide, right, whether to do a syscall or um, a separate call so that DMA is accessed.
Okay, first of all, let's clearly understand at, at what point, okay. So we are talking about your program has issued a printf or your program wants to do IO. So what time do you think we are talking about? Compile time or runtime? I hope you understand the difference between compile time and runtime. Like say syntax
Run,
errors are got at compile time,
right? Runtime, sorry. Yeah.
runtime. So the compiler is nowhere in the picture. Okay. We are talking about runtime of a program. So that's what confused me. Like the compiler is nowhere in the picture. Okay. So this question does not make much sense. Okay. Okay. Yeah. Anything else?
So when we say so that right, so the compiler is not in the process, right? Uh, I use the wrong word. So when it is compiled, when it is running, uh, all these, let's say syscall is getting called. So are there fixed number of processes? So which are these processes which get directed to DMA and which get directed to the CPU?
Again, I'm not sure. So DMA is specifically for DMA is usually for transferring. I mean, usually let's say associated with an IO. So those processes only or those programs which want to do some IO, they have to use the DMA for some reason, and also possibly the program itself will not use the DMA. The OS will handle it for them. Right. So I mean, when you write like when you want to print something, you just issue a printf command or a printf function. You just call the function. You do not even know whether there is a DMA in the background, etc. All these things the OS handles. So again, I'm still not sure about your question. So
Yeah, I thank you.
okay. So basically, in a modern day system, there are lots of processes or programs in the system, all running. Okay, let me correct myself. Don't think that all are running simultaneously. But again, let me go back to something that I just gave a small example last Friday. Suppose there are 50 users in the system, 50 users logged on, and they are running, let's say on average 2 programs each. So 100 programs or 100 tasks are running. Now, when I say 100 tasks are running, be very careful that 100 tasks are not running simultaneously. At one point of time, only one task is running. But possibly the switching between tasks is going on so fast that all those 50 users will feel that all their 100 tasks are running simultaneously. Like there were questions like how are we seeing the GUI? That means is the GUI running the program which is showing us the GUI? Is that always running? The answer is no. No one program is always running. I mean, at some one point of time, only one program is running, but this is happening very fast. Remember that analogy with Viswanathan Anand playing 50 students. At one point of time, Anand plays only one student, but he switches from one student to another so fast that every student feels that Anand is only playing with him or her. Similar thing happens here. You might think that all your programs are running simultaneously. That's not the case. At one point, only one program is running. Now, so your program can be doing, say, one of two things. One is it actually is running, so it is using the CPU to execute instructions. Second thing is it has requested for an IO operation. When it happens, then OS gives the DMA the responsibility of carrying out the IO operation, and your program is made to wait. It's made to wait because it cannot use the CPU now. Let's say the program is such that unless this IO operation is done, the next instruction will not be executed. Right, so that is what we also know. Like, so you have asked for an input from the user, a scanf statement. Without this input, you really cannot proceed in your program. Okay? So, I mean, logically, you might find that there are exceptions. You can write multi-threaded programs and so on. But in general, let's say your program waits until the IO is completed. So your program is made to wait. The DMA will control the DMA will do the IO. Meanwhile, the OS allocates the processor to some other program which is ready, which is not waiting for any IO. Okay. Fine. So Akshat is asking if you are printing some big file and also want to take an input. Okay. Okay. Again, see, fine. I understand your question, but see, if we are printing some big file and also want to take an input, till reading here, I first started thinking, how can you be doing two things together? But okay, then seeing the rest of your question, I understand that possibly what you mean is this, that one program is printing, another program wants to take some input. Right. So in general, if you start talking like in terms of we, then like who is this we, that becomes a bit difficult to understand. Right. So I mean, yeah, so try to frame your questions a bit more technically, that like we are printing, etc. Instead of that, say that process P1 is printing, or application A1 is printing, and application 2 wants to take an input. Okay. Okay, so fine. Okay, again, let me not go into details, but just let me tell you, DMA is only, so for the particular program application, for the particular situation you asked, Akshat, DMA will possibly not be even used by the second program. So DMA is mainly used for bulk data transfer. So yes, if you are printing if one process is printing a large file, then DMA will be invoked. But maybe if another program wants to take just a small input from the keyboard, I don't think DMA is used. DMA is only used for bulk data transfer. In such small inputs, some interrupt driven IO will be fine. And see, that can happen in parallel, right? Because as I said again, when the DMA has been put in charge of the print operation, CPU does not need to worry about it anymore until the DMA interrupts and tells that the IO is over. Rather, the CPU has allocated, rather the OS has allocated the CPU to some other program, and that program asks for an input. So fine, it can take that input. Now, if you are asking if two program wants to print two big files at the same point of time, again, not at the same point of time, that is not possible. But suppose program P1 is printing a file, program P2 also wants to print a file. Now, from common sense, these two operations cannot proceed together if you have one printer, right? So definitely it will have to wait for some point at some point. Okay. Okay, any other question? Okay, in the interest of time, let me move ahead. So yeah, let's start with the the second slide desk, which will also, I guess we will keep answering these questions. So after this particular slide deck, maybe you will have a bit more clarity about what is going on. So let's proceed. Okay, sorry. Okay. So this is what we have discussed till now, like what is an OS, the goals of an OS, basically the two major goals being making it easier for the users to use the computer system and efficient utilization of the resources, including the CPU mainly. And we have discussed the two key parts of the OS, the kernel and the rest. And we have also started discussing the interrupt-driven functionality. Now, in this class, we will first do a brief historical overview of OS, but we are just not doing this to tell you about history. As we tell about this history, you will see how computer systems have progressed, how they have become better, and that will actually give you some idea about the different key ingredients of an OS as we know it now. Right? So let us start with the historical journey, but believe me, it's not completely history. There will be a lot of things to understand in this historical discussion also. Okay. So initially, like long back, computers were simply devices which perform one computational task. So typical things are what we still see in a calculator. Give it one job, it will give you the output. There is no question of even having two jobs at the same time. A calculator, you just give it one calculation, it will do. After it is finished, you can give it the second calculation. Right? So only one job at a time used to be processed. And these devices are still there. They are very simple. Now, computers were also once like this. Only one job at a time. In fact, maybe some of you have heard of systems produced during World War I, etc. Things like ENIAC. Right? Even in those machines, there were computers, early computers, but they could do only one job. So the whole ENIAC machine was built for only one job. And so there was no question of having multiple jobs at all. But then, naturally, like mankind wants to improve systems and make them faster and easier to use. Therefore, naturally, people started to wonder, what if we had multiple jobs to compute? Then, the first computers came where the operating system was very simply designed. Again, this was very similar to the devices which I showed in the last slide. So at that point, the point that we are talking about now, even computers were like calculators, only one job at a time. So this was usually called batch processing. So there was a small operating system, but basically it did not do much. So basically the memory at that point looked like this. Maybe the operating system occupied one part of the memory, and only one user program used to be loaded in the other part of the memory. And the other jobs would be all waiting. Waiting for what? For this program to complete. So only one job is in the memory at a time. It is executed till completion. Then the output is given. Then the next job is started and so on. So there is this queue of waiting jobs and only one program at a time is executed. So then the operating system was so simple. No need for maybe all these interrupt, etc. etc. Operating system just had some way of figuring out when this program ended, and then it could load the other program and then start it. And as long as so then what is the issue? So this is a very simple program. This is a very simple system. But what is the issue? The issue clearly is that very high waiting times. So a job has to wait for another to finish. Right? And basically underutilization of the CPU. And why underutilization of the CPU? Because at that point, the input output from peripherals were very, very slow. In those days, remember, we were talking about not USB drives and hard disks. Then we had magnetic tapes and those kind of punched cards, magnetic tapes. They were very slow. Right. So suppose so in those days, programs were also quite simple. So maybe it is not that the program execution requires more time, but the input output required huge amount of time. So if my job is executing now, your job, which is waiting in the queue, has to wait forever when my job is simply reading the necessary data from peripheral devices. So it was quite the case that my job required 20 minutes to run, but out of that 18 minutes were only for I/O, input and output, and only 2 minutes were for processing. But then your program would have to wait for all those 20 minutes. So that was clearly bad. So we will soon discuss what better options, but even here, try to understand this, that a typical job usually has two types of phases in its lifetime. Some phases when it uses the CPU and some phases when it does I/O. Okay. In these systems, which we are discussing now, very early systems, there was no distinction made between these two phases. A job used to be allowed to run or used to be allocated the CPU both during this phase when it is using the CPU and also during this phase when it is doing I/O. The CPU completely used to be allocated to this one job, irrespective of which phase it is in. And that is why all the other programs had to wait until this job is complete. Okay. Designers quickly understood that this is a big bottleneck because these phases require a lot more time, the I/O. So then they began thinking, okay, I have one processor, fine. So when one program is using the processor, clearly I cannot run another program. But when one program is doing I/O, can we run another program? That will at least bring down the waiting time. Okay. So that led to development of slightly better systems. The next systems which came up use something called spooling. Okay. So the full form of spool is simultaneous peripheral operations online. Spool. So let me explain what a spool is first. A spool is a buffer that holds output for an I/O device. Usually a device such as printer that cannot accept interleaved data streams. Right. So remember this was still older times. About say half an hour back I told you about a local buffer in a device controller. You might think this is a 40 years older version of that. Okay. Nowadays there is a device, every device controller has its own local buffer. 40 years back, the simplest version of that was a spool, a buffer which holds output for an I/O device. So basically it used to be used for the following: read as far ahead as possible from input devices, or store output devices until the output devices are able to accept them, and so on. Why do you think it is being used? So suppose the suppose your program is only using or only processing input line by line. But so basically this is the caching kind of thing. So it is processing your data. So your program is processing data line by line. But while reading every line, it does not want to go to the I/O device because I/O device is very slow. So rather, maybe read 100 lines from the I/O device and store it in this pool. And then when your program wants one line, just give it that one line. Then it asks for the next line, give it the second line, and so on. Right. So that is how a spooling is to be used. So essentially, the idea is that again reduce I/O time by inserting something like a cache. This is not cache, but the idea is similar. I/O takes a lot of time, and therefore, so I guess you see the analogy. Cache is between memory and CPU, and spool is between an I/O device and a CPU. But the idea is simple. The CPU is much faster than both memory and I/O device, so you need some buffer in between too, so that the time of CPU is less wasted. Okay. So people started trying out these kind of techniques to reduce the I/O time. So basically spooling looks like this. The CPU now does not, okay, so this is the picture. So this is the I/O processor which handles the I/O devices. Now the CPU does not directly talk with the I/O processor, but there is this spool in between. So as I said, suppose a large file is to be taken as input. A large part of it used to be read and stored in the spool buffer, and then the CPU could access maybe one line at a time or something like that. Similarly, during say output, the CPU could store quickly much data in the spool buffer, and then maybe some I/O processor used to access this spool buffer to do I/O. Meanwhile, the CPU did not need to focus on this IO. Rather, it can be allocated to some other program. Okay. So this was so as you see, people understood this problem that IO is taking a lot of time. Therefore, the quest started, or people started wondering, can we reduce the involvement of CPU in the IO so that when one program is doing the IO, can the CPU be allocated to some other program? This, okay. So this led to the development of better systems. But even from this pooling, so this pooling was a like lot old system, very old system. But even from this pooling, you understand about some important concepts. First, addition of IO processors. These were very early IO processors, the modern versions of which is possibly the DMA. Basically, IO processors were kind of assistants to the CPU to only do the job of IO, but with as low involvement of the CPU as possible. Right? So the read-write became a bit faster, and this was most important. The IO of one job could be overlapped with computation for other jobs. Okay, this was the main key factor which led to the improvement of computer systems. That IO of one job could be interleaved or could be overlapped with computation of the other jobs. Okay, let me stop here today. We will continue from this point tomorrow. So any questions? Maybe for a couple of minutes. Slides will be given, but we would like to give the slides after one deck is over. So today the first deck got over. We will give you the slides. Any other question? Okay, if not, then fine. Then let's break today. We will continue tomorrow. Okay, Abhijit has a question, but IO is still there, and how is it reducing the time? Of course, IO has to be there. Like even today, we cannot say that IO won't be there. Programs need IO. The question is, so there are two parts of this question. One is, yes, IO devices are getting faster also. IO devices are getting better, but I don't think you are asking about that. I guess what you are asking about is, we are not talking about reducing IO time here. We are talking about reducing the involvement of CPU in IO. It means we are trying to separate out IO and CPU. When one program is doing IO, even if that IO might take a long time, but then that program has to wait. What we are going for is, when one program is doing that IO, can I allocate the CPU to other programs? Okay, so we are not specifically talking about reducing the time for IO here. Of course, mankind has also done that. Nowadays, the IO systems are much faster than what it was 40 years back. As I said, then there were magnetic tapes. Maybe writing 1 kilobyte of data required a lot of time. Nowadays, IO devices are also a lot faster. So that way, we are reducing IO time. But I don't think we are discussing that part here. We are discussing that IO will take time, but can we reduce the involvement of CPU in that IO so that the CPU can be allocated to some other program when one program is doing IO. Fine, so I don't see any more questions. Let's leave here, then we will continue tomorrow. Thank you.